Okay, we're back. Hello, everybody. Let me play some tunes. Get locked in for stream. Oh, uh, hello. Today's a little bit of an unexpected stream because I was supposed to stream tomorrow at 6, but so I was supposed to have beach volleyball today at 6, but it got canceled because of the weather, even though the weather's pretty good right now. Apparently, there were some people sick, so I postponed it to tomorrow. So I decided to reschedule, and we're streaming today instead of tomorrow. Sounds good? I don't care if it isn't, because I'm doing it anyway. But yeah, hello, thank you everybody for joining today. Today we're gonna do some LeetCode mediums from Grind 75 again. And yeah, I'm very tired. I think I posted on Instagram. I'm on like 1% battery right now, and I mean like sleep, like tiredness battery. I was supposed to go to the gym. I got home at like 5:30. I was supposed to go to the gym before stream. I was like, I am feeling it. Maybe I'll go after stream. It's just because like I just ate something before, like when I got home, and I was like, my stomach isn't really, you know, prepared for gym. Maybe after. I don't know. We'll see. But today, as you can see, stakes are high. Because we're doing, I don't know, like I feel like the problems are getting harder. So today we're gonna do LeetCode mediums. It's just 2 LeetCode mediums. We've been doing LeetCode mediums for like a couple streams, so it'll be fun. It'll be fun. Grand Site, I don't know. LeetCode mediums, I feel like they range from like really easy to really freaking hard. So we'll see what we find today. But yeah. And then tomorrow I will go to beach volleyball. So there's no stream tomorrow like it was supposed to be, unfortunately. But we're here today. Anyhow, so I'm gonna get started. I think probably gonna do, if I don't get stuck on the problem, I'm gonna try to do like a little bit of a shorter stream. Like I said, I'm kind of tired. And then we'll be back, what is it, Wednesday? We'll be back Wednesday to do the RAG project. Hey Medfi. I am currently working as a software engineer. Like I just recently graduated and I started this job like 2 months ago. I started these streams before I got that job, and the whole point of it was to like practice to become like a better software engineer and to be more prepared for interviews. Um, but I decided to keep doing it like after I got this job. I think it's like good practice. I like doing competitive programming. I like staying like practicing, doing personal projects, and just doing these streams just help me like keep accountable and keep practicing weekly, like on like a schedule. So that's the whole reason. Like I'm not in like pressure like to like do anything. But I do enjoy doing LeetCode. And I think just staying on like on par with like, because if you stop doing it you kind of lose practice and then you have to redo it. So I just never stop doing it, and that way if I ever need to do another interview, I don't have to practice for it again. So yeah, it's a little bit of a long-winded answer of why. But yeah, anyway, so I'm gonna get started like always with the Arcana card of the day. And that is Dashpar Dodgeball Dynamo. It's a 1-cost inkable card. It has 1 strength, 1 willpower. It's a storyborn superhero. It's from The Incredibles. If you haven't seen that, you should. And it's evasive, and quest for 1. It's by artist Mike Parker. It's card 114 out of 207. In English from set 13, it's an uncommon card. And it says, the flavor text says, hey, look here. Hey, look, I'm here. No, wait, I'm over here now. Nope, back here again. So, this card, very, like, vanilla, but it's decent. Like, it's a good card to, like, start, like, having evasive on turn 1. pretty good. There's other similar copies of this. Like you have Pegasus in green. This one cost 1/1 effect evasive. That's inkable. So over like these like inkable cards are like evasive cards for one are pretty good because you get to like quests pretty much with no contest very early, but they're not like crazy. So yeah, right now there's three of them. So there's Dashpar in red. There's Miko, and Miko quest for 2, so it's a little bit unique in that sense. And then there's Pegasus, which is just the same as Dashpar. And because Miko quest for 2, and it's also evasive, it happens to be an inkable, so that makes it a little bit more balanced. And also has an effect that if you don't discard, if this card is exerted and you don't discard at the end of your turn, you have to banish him. So that kind of makes it a little bit more balanced. But this is also very good in like really fast aggro. But yeah, today's card was very balanced, but pretty decent. Like if you're playing something where you can use this and kind of aggro early, it's good. Anyway, let's get started with the LeetCode. Okay, I'm just gonna set up my desktop. Okay, so today we're solving search in a rotated sorted array, and we're solving combination sum. So we'll start with search in a rotated sorted array, and it says there is an integer array nums sorted in ascending order with distinct values. Prior to being passed to your function, nums is possibly left rotated at an unknown index, such that the resulting array looks something like this, 0 indexed. For example, 0, 1, 2, 4, 5, 6, 7 might be left rotated by 3 indices and become 4, 5, 6, 7, 0, 1, 2. Given the array nums after the possible rotation and an integer target, return the index of target if it is nums, or -1 if it's not in nums. You must write an algorithm with O of log n runtime complexity. So they give us 3 examples here. First one is this nums, like this is the one I think they give here. And then you're looking for 0, and you basically find it. This one you're looking for 3 on the same array. Don't find it, so -1. And then you're looking for 0 in this array, and you don't find it, you're -1. And so, a couple of clues that they give us here on how to solve the problem. The biggest of them all is you need to solve it in O of log n. And we solved, where is it? Oh no, it's all good. Like I'm not in the middle of the problem or anything, and I don't mind something to answer. But basically, what you're saying. So what I think about that is probably if you're giving me those two options, good projects are probably gonna be. It depends on what stage you're stuck on right now in your job search, right? So if you're right now you're stuck on the stage where you can't really get past the resume review, and like getting like past the like HR screening, then I would recommend focusing on projects because that probably means your resume isn't strong enough, and if you don't have the opportunity to gain some experience to showcase that better on your resume, projects are the next best choice. Also, but before you even like start doing projects, just see if there are ways in which you can improve your resume to get past that stage. So if you're in university, when you mentioned you're a fresh grad, I would get in contact with your career services and help them listen to review your resume to like organize it a little bit better. And then if I would maybe get in contact to see if there's anybody that you can sort of find like a mentor that's maybe already in the tech industry that can review your resume and tell you where there are weak points and where you can make it better for the roles that you're applying for. That's part one. Part two is if you're not stuck, like if you're able to get interviews, if you're able to get past that, but you're getting stuck in the technical interviews, then I would focus on LeetCode. I understand that it's annoying and a lot of people don't like it, but unfortunately the reality is that you sort of Yeah, I mean, just the market is hard right now. I wouldn't like leave away lead code. I think it's important, but like take that with a grain of salt because the industry is moving a little bit more towards like different types of interviews. Like I think HackerRank just updated their platform, and now the problems are a little bit different, and people are moving away from like lead code interviews. And I say this from experience. By when I was applying for jobs, I was seeing less lead code problems and more like different types of problems. I still would like practice a little bit, like at least just do like grind 75 or like a like neat code 75 or something, like do like a list of like the most popular problems and know those because they repeat them often in like different companies. But if you're getting stuck more on like the not getting interview stage, just work on your resume a lot, and then also work on some other stages. So very underrated, but I know people say it a lot. It's like networking is very important. You By doing just a little effort, you can stand out amongst other candidates by like emailing hiring managers, by like going to networking events in your university or in your city. You can get in the minds of like those people, or like they can connect you to the right person. So there's a lot of work that you have to do, and it's unfortunate because of the like the point in like the economy that we are right now. But it's just something you have to accept and deal with. And yeah, no, I wish you the best with like the job searching. It was hard for me. It took me like 6 months, but you got this. You just gotta like keep working on your stuff, keep showing up every day, become a little bit better every day, improve your resume, all that stuff. Um, Anyway, so the I was saying here that like the trick, like the hint that they give you to resolve this problem is that they say that it's a login runtime complexity, and that looks a lot similar where we're looking in an array for an element and checking if it's there or not, and then returning the index. That looks a lot like binary search, which we solved like pretty much almost at the beginning of this series. But there's a twist here in that your array is rotated. And so you can't just run binary search because the sortedness of the array doesn't hold anymore, right? Like this array technically isn't sorted in, in this form. It's sorted in the original form, but it's not sorted in this form. So you can't just run binary search as this. Um, it says it's possibly left rotated, so they could hand you just basically a sorted array that has not been rotated at all. So there's kind of um, like there's kind of that case you have to handle, which we'll find out that you don't really have to handle that separately. So um, yeah, thanks, Matvi. So here the trick. I mean, I don't know how would you come up with this initially. Um, the trick is like they tell you it's log n, so you know you have to stick within like algorithms that like cut down in half every time, like binary search. So I would look like think of algorithms like binary search or like divide and conquer. Divide and conquer is some of like more like advanced. So most of the time, if you're being asked for log n, it's normally you have to run some sort of binary search. And here we'll find out that to do it in no of log n, we just basically run binary search 2 times. So for the first time, we need to find the point in the array that is the first index. Um, and once we find that point in the array, so we have to find this, that is the first element in the array. Once we find that point, then we know what our left and right indexes are now that it's rotated, and we can run regular binary search there, right? So we have to run binary search here to find the first index, where this being like where let's say this is index I and this is index j. The number of and the index I is bigger than the number of index j, because if you see this part is sorted and this part is sorted, but this part is not. So we have to find this part in order to find the first index that is not sorted in the array. So now we know what the offset is, and we can either, well, you can't just reconstruct the array because that takes all of n, so you can't do that. But what you can do is, now that you know the offset, you can do your binary search with that offset. So I'll show that in a second. Let's first, so this is gonna be, what kind of problem would this be? Like an array problem? Where do I have binary search? Binary search is problem 704. Oh, I don't have that here. Okay. 700, oh wait, no, that's not the right. 704. Yeah, I have an array. Okay, so let's do it here. And then we're creating a new file, and this is 33.cpp. Okay. Now, we are going to copy this, paste it here. And so first of all, well, like I mentioned already, we are running binary search at the end of the day. So let's just create the function for binary search. And I'm gonna do it recursively because I can. So int binary search, int L, int R. This is gonna be our regular binary search, and then are we doing it this way? Sure, why not? So we get L, R, our target, and then we're gonna pass the vector here. And we pass it by value, so we're not copying over and over and over. So, if okay, so first we calculate the mid. So int mid equals L plus R divided by 2. Round it down because it's C++. And now we check if num's mid. So if the number in the middle is equal to target, then we return mid. If the number in the middle is less than target, then we're gonna binary search on the right half. So we run binary search on m+1 r target nums. Return binary search on there, and else we're gonna return binary search on L, m-1, and target, and nums. There's another thing here. If it, like, if our indexes are no longer the same. So if L is bigger than R, then we return -1. That means it isn't in this array. Like, we went through all the possible indexes and it isn't here. So this is our regular binary search, right? So this works if the array has not been rotated at all. Now, let's do the second binary search, and let me run through an example here. So let's take the example that they give us here. So 4, 5, 6, 7, 0, 1, 2. 4, 5, 6, 7, 0, 1, 2. Okay. So, let's think. How do we do this? Okay, so we pick left and right beginning, like the whole array. We're searching the whole array, and then this is going to be our middle, I believe. So it's 1, 2, 3, 4, 5, 6. Sorry, it's 0, 3, 4, 5, 6. It's 6 divided by 2 is 3, so this is index 3. So we look at 7, right? And now we can do one of two comparisons. We can compare it against the previous index, or we can compare it against the next index. Um, hmm. It's going up. Okay, let me think for a second here. Um,
First of all, what went through my mind is how stupid am I to actually volunteer for this?
so if okay, let me skip the song. Okay, so there, let's compare it against the previous one. So it's left rotated. Okay, so how do we find the first index? Oh, brother, you're more locked in than I am, but thanks for joining. I'm at like 1% battery. I'm so tired. And I've gotta solve LeetCode problems. Okay. So we have to find the breaking point in O of log n. How do we do this? I was thinking you compare it to the next number, and if it doesn't hold, you know where the break is, right? But if it holds, if it's still sorted, then where do you go? Do you go left or do you go right? And that is the problem. Focus, focus. Okay, I will. Um, okay, so it's left rotated. So we're always gonna have. So it's always gonna be like something like 2, 3, 4, 5, 6, 0. It's always like the beginning, it's always gonna be after. So if at this point is sorted, we go to there. Okay. It's not numbered, right? All of the numbers are unique. It's ascending that is possibly rotated. Could it be to the left? Could we have something like 7, 0, 1, 2, 3, 4, 5? So, okay, let's see these 3 cases. So, in the cases here, we should move to the right to look for the rest because this is sorted, I guess. In this case, this is sorted, so we should move to the right. In this case, this is sorted, so but we should move to the left to find the first index. Can we use the first and last element to do something about this? Okay, so here the first and last elements are 4 and 2. Okay, and if the array was not rotated at all, it holds true that this is bigger than this. Always, yes, it has to be. If the is there any case in which that holds but the array is not rotated? If the array is rotated. So if we left rotate this, then it wouldn't hold, right? Yeah, because this first element would be somewhere like in the middle of the list, while the last element would be somewhere here. Like it wouldn't hold anymore. Mm. So can we use that fact to find the first element in the array? So, oh, okay. So maybe here what we're doing is, so let's say I don't know for sure yet, but that is my hypothesis that if the array is not rotated, then the first element is always going to be less than the last element. But if it is rotated, the first element is going to be more than the right element. So therefore, we can use the middle to pick the beginning element of the beginning element of the array. So we pick 7 to be the beginning, and we do the rotation. So basically, the trick to the rotation, which is kind of what we're gonna use later, to like reconstruct the original array without actually building it. Yeah, I feel like, yeah. Um, but they don't actually teach us this, which is kind of sucks. So if we pick here, and so we're gonna pretend that we can magically rotate this, and I'll teach you later how to do it. That we can magically rotate this array, um, like this to the beginning. Basically, we're left rotating it 7 to be the beginning. So we're gonna have 7, 0, 1, 2, 4, 5, 6, and now we're checking: is 7 bigger than 6? No. Well, no, yeah, 7 it is bigger than 6, so therefore um, this is not the correct rotation, right? Now, what if we had picked... Okay, but that tells us if it's wrong or if it's right. It doesn't tell us where to go from here. Do we get any other information from the problem? Because, okay, here we're supposed to go right. It's not going to be in this half. Can we use the LNR in that case? I'm assuming we can when we have to. Okay. Let me think. So let's do 2 examples. So in this case, we're supposed to go right. Let's do an example where we're supposed to go left. Let's say we have something like this array. Oh, my bad. We're doing search in a rotated sorted array. So basically, we have this array, right? And we're trying to find a target number. So in this case, we're trying to find 0. And we're just basically, if that number is in the array, we return the index. So in this case, it is in the array, so we return the index, which is 4. 0, 1, 2, 3, 4. And if it's not, we return -1. The trick, the like twist here is that the array is rotated. It's sorted, but it's rotated left, right? So they took this array and then they rotated it left 3 things. So now instead of 0, 1, 2, 5, 4, 5, 6, 7 is 4, 5, 6, 7, 0, 1, 2. So it's rotated a little bit. So we have to find the target, if the target element is in there in the index, in all of log n. So we need to do some sort of binary search. So my hypothesis is that you can run 2 binary searches, one to find the first index and another to find the actual element. Like once you know what the first index is, you can just run binary search on that rotated array, and that should give you, like, you just do regular binary search. The trick here is to find which is the first element. Okay. So let's do it in this array. We pick here, but we're supposed to go left, right? Um, okay, I see something here. So in here, 7 is bigger than 2, bigger than this right element. However, here, 2 is smaller than 6. I think that's what gives us if we need to rotate left or right, right? If the middle is smaller than the right, then that part is sorted, and the unsorted part is going to be to the left. So that's where our first index is. If the middle is bigger than the right, then the right part is unsorted, and we need to search on the right side, right? How do we know if we are in the beginning element? Here it's sorted, and then until we just get to the end. So here, okay, let's do the example with this one. We're here. This is less, so we search on this portion. Could it be this element? Yes, this could be the element. Like, for example, if we had, instead of this, what would it be? Chun chun. So I think it would be like 5, 6, 7, 0, 1, 2, right? So we get here, 0, there should be another element here. Oh, there's a 4. 0, 1, 2, and 4. So we get here, we see that this is indeed less than this, and now we take this half. And so we keep this element until we find something that contradicts our hypothesis, so we find something more to the left. If we find something more to, like, if we say, okay, so if this part is, sorry, if, let's go back to this example. This part is not sorted, so we know this is not the beginning element, because if this was smaller than this, then this could be the beginning element, right? Like in the case we saw, like in our sorted array, 0, 1, blah, 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 7. When this is less than this, like this could be the beginning element, right? But if that's not the case, then it's either the element I'm currently on or something to our left. I'm gonna try and make sense of it, and then after I'm done with like the implementation, we'll do like a more in detail explanation. Okay, so here I'm just gonna do this. Should I do this in a separate function? Nah. Okay, so LR, so L is gonna be equal to 0. R is gonna be equal to nums.size minus 1. And when we do a while, we're gonna keep like the last element that worked. So I don't know, like we're gonna call it begin index, begin IDX, and it's gonna be equal to mid. Let's call it minus 1 to start, because we don't know what that index is, so we'll initialize it to like empty. And then while L is less than R, let's say for now, that condition might change depending on how this while loop ends up working. Then we calculate mid. So the mid is going to be equal to L plus R divided by 2. And now if middle is less than right, then middle could be the beginning index, so we'll just call it middle is going to be equal we call it the least element, right? So we're always going to override it. They're all distinct, right? They're all distinct numbers. All numbers are unique. Okay, that's fine. So middle, sorry, not middle, begin index is going to be equal to middle. right? Else it's never gonna be the same. And actually, this should be nums are m and nums are, not m and r. If nums m is less than nums r, then that could be one of our working indexes. Otherwise, we're gonna search on the right half. So, and also here we're gonna make r equals m, and then here we're just gonna say L equals m plus 1, because it doesn't include the current number that could be the beginning index. I'll explain it better in a second. Just bear with me. R equals m. So technically, yeah, this should be L less than R, because when L becomes R, then okay, we need to do like a final check here. If num L is less than, not nums L is less than nums R, then begin index equals L. Oh, also this binary search, the trick, we need to do modulo. So this is gonna be mid percentage nums.size, or modular nums.size. Modular nums.size. Okay, just bear with me 1 second. I'll explain it all at the end. I'm just making sense of this and making sure this works before I start explaining and it ends up not working. Okay. And at the end, we're gonna just nums percentage nums.size, nums modulo, I keep forgetting. And then at the end, we're just gonna return binary search of begin index, and then begin index plus nums.size, and target and nums. Okay, well let's see if this works. It's probably not gonna work first time, but okay. Where's num? Identifier m. Okay, so m should be mid. Mid. Let's see. Infinite loop. Okay. Let's just put it here. What do you mean I'm submitting too frequently? It works. Oh, I'm the greatest programmer ever lived. How am I so good? Okay, I'm gonna submit and then I'll explain. Okay, never mind. I'm not the greatest programmer that ever lived. So in this case, it moved to the right. Okay, so this should be, actually, if L is equal else if L is equal to, sorry, if M is equal to R, then begin index is equal to R. Let's see if this works. Hmm. Is that always the case? L equals to, okay, so if I'm here and then I move to the right, then that is true. But if I move to the left and it is not true, okay. So there's two cases, right? There's the case where we had 3, 5, 1, where here this doesn't hold true. We look to the left, and this is always the right number. This is always the beginning number. However, there's another case that we have that is 1, 3, 5. This holds true. We look to the left. We look to the left, but we still keep this index. So then this moves to the right, and then that becomes true. So we don't really need mid. Like the beginning index is always gonna be at like whenever they converge, L and R converge. So we do need mid for the calculation, but we don't need begin index. This is just gonna be L, I believe, and then L, whatever they end, wherever they converge, because that's what's gonna get us out of this condition. Out of this condition when they converge, there's nothing else that gets us out. Where's begin index? Right here. So we don't need this. Okay. Okay. Fine. I'll explain it now. That took a little bit of time, but okay. So here is what we are doing. Let's go back to the beginning example. Right. So we begin. So we note a fact here, and that is we have two portions of the array. Right? We have the right portion and we have the left portion. Right? This might shift somehow, so like you might have 1, 2, 4, 5, 6, and then 0. So your left portion might be this, and your right portion might be this. But you're gonna have two portions, like the half that's from the beginning to the middle, and then the other half that's from the middle to the beginning. Okay, that's your first fact here. Now, another fact. If we're looking at a subarray, or like the whole array, the subarray could be the array itself. Okay, let me not confuse you. If we're looking at an array, we can know if it's sorted completely and not if it's not rotated, basically. If the left is smaller than the right. Like if we have 0, 1, 2, 4, 5, 6, whatever, the left is always going to be smaller than the right. And in any other case where it's rotated, the left is going to be bigger than the right. So that's how we know if it is rotated or not. Now, how do we know where to go? Right? So if we're looking, like when we're selecting here our middle index, we're selecting this as middle. We're basically saying, is this the first element in the array, in the sorted array? And we basically, to check if it's the first element in the sorted array, we're checking, is this subarray sorted? If it is sorted, then okay, in this case we're checking this subarray, including the middle. Is this subarray sorted? If it is sorted, then that means that that like everything from here on out, the beginning is not going to be, right? Because if the beginning element, sorry, was to the right of this element, then this condition wouldn't hold true. Like this wouldn't be a sorted array, because we would have like this right portion here, and this condition doesn't hold true. However, if we had something like this, and we check here, this subarray does hold the condition that this part is sorted. So we know that our beginning element is going to be either the one we're currently at or to the left. I don't know how to explain this better. It's sort of a hard thing to approach, but that's how we're basically running our binary search. So if the portion, if the subarray starting at the middle and ending at right is sorted, then we know the beginning element's not going to be there. Like in this case, we know the beginning element's not going to be here because this part is sorted. So that means the unsorted part is going to be here, including the current element. We have to include the current element because this could be the beginning element. We can see that with an example. So we have 5, 6, 0, 1, 2, 4. Actually no, it would be 4, 5, 6, 0, 1, 1, 2, 4, 5. I feel like I'm missing an element. Does it go to 7? Yeah, it goes to 7. Okay. So it would be 5, 6, 7, 0, 1, and 0, 1, 2, 4. So if we fall here, and we see that this is sorted, then this could be the beginning element because of the thing I told you about. Like in a sorted array, the left is always less than the right. So this could be our beginning element because the left is less than the right, and like this part is sorted. However, it could also be behind me. Like it could be this is part of the sorted part, like part of this part, but it's further to the left. So if we get to if we're checking like this element first, we see that it's sorted. So now this is the array that we have to check, because it could be this, it could be this, or it could be this. Like in the case of a sorted array, so we have 0, 1, 2, 4, 5, 6, and 7. We come here, this part is sorted, but the beginning could be anywhere in this part. I don't know what this is called. This is a special type of binary search where you start like trying to find the minimum index. But yeah, so those are the two rules basically. If my left is bigger than my right, then that means the unsorted, so like in this case, my 6 is bigger than 2. So my unsorted part is somewhere to the right of this element. And we know that this is not going to be the beginning element, because if it was sorted, this would be smaller than this. So we can like not include this element and just search here. And then we pick a new middle, and we're just trying to find the beginning element. And then we do another trick, and that is once we find the beginning element, so we find this 0, then how do we rotate the array without actually building the array? Because if we build the array, like if we start from this index and we build 0, 1, 2, we build the array, that's O of n to like copy it. So we need to not do that. So we use an operation called modulo. So we put this as the L, and then R, we count the amount, like an offset of the amount of elements from here. So we're basically repeating the array. So we do 4, 5, 6, 0, 1, 2. We're extending the array, kind of. So we put this as our L, and then imagine this was an infinitely repeating sequence. So you put 4, 5, 6, and 0, 1, 2, 4, 5, 6, and etc. Imagine this is an infinitely repeating sequence. Then if we put L here and we put R, like there's 6 elements here, so we put it 6 elements after this one. 1, 2, 3, 4, 5, 6. We put it here. Then it's just like if we had the original rotated array without actually rotating it. And how we're achieving this infinite sequence is with an operation called modulo. What modulo does is once it reaches R, it basically gives you the remainder of an operation. So we do everything modulo R. And so if we have L being 0, 1, 2, 3, and let's say we want to access L plus 3, so index 6, there is no index 6, it only goes up to 5, 0, 1, 2, 3, 4, 5. So once you get here, modulo kind of like resets it to the beginning. So it makes this infinite sequence by just like giving you the remainder and putting you back at the beginning. So it's just basically like a function that makes numbers like this, like 0, 1, 2, 3, 4, 5, 0, 1, 2, infinitely repeating. Like it can't be bigger than this. So we're using this modulo operation to basically find our rotated array, like our original array before rotation. I don't know, this is kind of hard to explain. It makes sense once you do it and you find the trick. I had to think about it for a little bit because I haven't solved it since November 2024. But once you solve enough of these, you kind of like, it becomes a little bit more natural to solve them. Okay, so now we're going to combination sum. Okay. So let's read the problem. It's problem number 39, combination sum, and it says given an array of distinct integers, candidates, and a target integer target. Again, we have a list of numbers and then a target. It says return a list of all unique combinations of candidates where the chosen numbers sum to target. The chosen numbers sum to target. You may return the combinations in any order. So we have to return the list of combinations, right? The same number may be chosen from candidates an unlimited amount of times. 2 combinations are unique if the frequency of at least one of the chosen numbers is different. The test cases are generated such that the number of unique combinations that sum up to target is less than 150 combinations for the given input. So we have, these are our candidates and our target is 7. And so here one possible combination is 2, 2, 3. Another possible combination is 7. And yeah, I don't have much to say besides that. Like, it's just you're giving, like, you can think of this as like coins. So you're given like these coins, and then you say you have an unlimited amount of coins, and you're trying to find if you can add up to this amount using those coins. Okay. So let me think how we're gonna do this. Okay, so let's copy one of the examples. All right. So this is a dynamic programming problem because you're trying to find like the combinations that make up to some target, and there's, if you think about it, there is intermediate solutions that you can use to build the final answer, right? So if you think about it, what are the intermediate solutions? Okay, we have target 7. So how do we find the what is the name of the function? How do we find combination sum? I'm gonna call it CS of 7. Well, we find the CS of 7 minus 2, the CS of 7 minus 3, the CS of 7 minus 6, and the CS of 7 minus 7. And what are these numbers? They might seem arbitrary. They're the numbers that they give us here, right? So if you find the amount, if you add all of these up, basically, so the number of ways you can, not the number of ways, the different combinations in which you can reach 7 minus 2, 7 minus 3, 7 minus 6, and 7 minus 7, and you add all of those possibilities, then that is going to give you all of the possibilities to find 7. Because those are all of the ways, like from 5 you can get to 7 by doing 5 minus 2, by doing 5 plus 2. From 4 you can get to 7 by doing 4 plus 3. Like, you know, you can get here from those indexes, so you just need to find how you can get to those numbers, and then you know you can get there, get to the current one. Okay. Now, I might do something that might not go into the constraints of the problem. I probably will. Yeah, the numbers are a little bit small. Okay, so my proposal is so if we're kind of like going from 7 down, I like to build like these dynamic programming solutions iteratively, like bottom up than instead of top down, just because it's harder and like it's easier. It's not easier. I find it that I understand them better once I do the bottom up solution, but the recursive solution is also valid. But if you think about it, what is our base case? What is the number? What is the target sum that we can always reach, regardless? And that is 0. We can always reach the target 0 by not using any coins. So our solution for combination sum 0 is just going to be an empty array, because you just don't take any coins. So we start from here. Now we build upon the solution using our candidates. So using each of our candidates, we start building it up. So what is CS of 0 plus 2? Well, that is basically, you just take this array and you append 2 to it. So 2. What is CS of 0 plus 3? Same thing. It's just if you were at 0, and then you take 3 as a coin. What is CS of 0 plus 6? Well, you take 0, and then you take the coin 6. And what is CS of 0 plus 7? You do the same thing. Now this is not our final answer, because we can get to like these later amounts Like, I'll show you in a second. So now for each of these, then you do the same branching, right? So this had like 4 branches, right? That are these 4 branches. And now for each of those, we also branch 4 times. So 2, we can add 2 again. So CS of 2 plus 2, CS of 4 is going to be equal to if we append 2 to all of these, which there's only one of. CS of, now we do 3, CS of 5 is basically 2 plus 3, and so on and so forth. Now, for this CS of 5, so we're going to write down this, and then we're going to skip the other ones for now. A limited number of times are unique if the frequency of at least one of the chosen numbers is different. Oh, okay. There's another problem. Numbers can go from 2 to 40. Okay. So, here, let's skip all of these possibilities for now. Now, here we do CS of 3 plus 2, which is CS of 5, and we find another possibility. 3 and 2. However, the problem tells us that these are unique only if the frequency of at least one of the chosen numbers is different. Here, the frequency of our numbers is the same. So, it is not unique, unfortunately. It goes from 1 to 30, it goes from 2 to 40, okay. Yeah, and so that is how you do it. Now I'm thinking of another thing. And that is, if we want to count if they're different, then we should keep the counts. We should keep the counts of each of the elements. Like we should, for each of the middle solutions, we should keep an array. And since we only have 30 possible candidates, then we can just keep an array that basically keeps the amounts that we're using for each. So let's say we've used 0 of the first one, 2 of the second one, 3 of the third one. We keep an array like this, and then we keep how much they sum up to, so we don't have to recalculate that every time. So sum equals basically 2 times 3, 6, and then 3 times 6, 18. 18 plus 6 is 24. We keep both of these things. And we keep checking that the sum is not bigger than the target, because if the sum is bigger than the target, we don't need to keep checking down the branch. Okay, I'm thinking of implementation details. But I think it's better if we just start doing the implementation. So let's go to DP. And we'll go and create a new file, 39.cpp. Okay. So here, okay, so we're gonna create our mem. Our mem is basically gonna be like all of these intermediate results, right? And so our mem is gonna make sure that like when we have this solution already that has 2 and 3. When we find the solution that has 3 and 2, we don't keep calculating all of the other solutions because we've already found the solution before, right? It's the same solution, just in different order. So we're gonna make sure that we don't recalculate this. Like once we find this, we just like use the answer that we've calculated previously. Okay, so how we're gonna store our mem? I'm gonna decide to create, since we know that the target is up to 40, then we only need to store intermediate solutions from 1 to 40. So I can make, for a mem, I can create an array of 41. Well, it's not going to be an array of int. Okay, let's create a vector. We're going to create a vector of set. No, it's not going to be a set. It's going to be a vector of a For that solution, can you hash a vector? I should specify it's C++. Actually, I should be more clear here. Can you have a set of vector? C++. You can. Okay. So a set of vector of int. This is kind of confusing. Okay. And this is gonna be our mem. And we're gonna initialize this with vector of set, a vector of int, and this is going to be of size 41. And then we're going to initialize it with set of vector of int. We'll see if this works. Okay, so basically how we're storing it is the vector is going to be basically a vector of 40 numbers. So the position, the index 2 is going to contain a set, and a set because we want unique solutions, of all of the possible solutions for that sum. So this sum 2, let's say we find this 2, 3 solution, it will contain a set with 2, 3. Actually, it won't contain a set with 2, 3 because we need to find okay, this is fine for now, but it's not going to contain a set with 2, 3. It's going to contain a set with the frequencies of each of the frequencies of each of the candidate amounts. So it would be like 1, 1, 0, 0 because we use one of each of these. And that's what's going to determine if it's unique. Yeah, this is, I feel like there's a better way to solve this, but this is what I'm thinking of right now. Okay. And so our mem 0, we're gonna insert basically an empty. Actually, no, we're not gonna insert an empty thing. We're gonna insert basically an array with all zeros. A vector with all zeros. Vector int init equals I think I'm gonna be able to create it here as like an anonymous function. It's gonna be of size 41, and we're gonna initialize it with zeros. Wait, no, not 41. It's gonna be of size candidates. That size. And we're gonna initialize it with zeros. Now, what do we do after? So, So now we iterate from the beginning element to what is our target. Our target can be sum at most, right? I'm gonna end up finding that this can be done with like no memory. Anyway, our target is 40 at most. So we start from 0 until 40. Actually, until target. And then for each of the elements in the set currently, iterate over a set C++. Okay. So here for const auto, and this is gonna be a possible solution. But I only have to copy the whole array. That is not efficient. Yeah, this is not, I'm overcomplicating the solution. Because the way I'm thinking about it is like I copy the whole array and then I change one element, which is not great. How else can we do this? Maybe this is just better suited to be a recursive solution. Because I can think of the recursive solution. Wait, can I? You still have to rebuild it in the recursive, and basically I can backtrack. So it makes it so I can use just one array. Can I backtrack in this, or do I have to keep all the possible options? I kind of have to keep all the possible options, so memory-wise it's not amazing. Maybe it still fits. Okay, listen, I'm gonna do it this way, and then if it doesn't work, we'll do recursive. Okay? So we're iterating over our set, and then each of these is gonna be a vector of int that's gonna contain our frequencies. And this is gonna be mem of I. How do you do a copy? Deep, actually just be a copy of a vector. How to copy a vector. So this doesn't, oh, this copies it? Okay, fair enough. Okay. And then for each of my candidates, I less than candidates dot size. Actually, this can't be, let's do it J. This is so inefficient. This is better suited for a DFS. For each of my candidates, I add them to all of the solutions. Okay, so maybe this should be the outer loop. Yeah, that should probably be the outer loop. So here for each of my solutions, actually, if I plus candidates j is bigger than target, return, no, actually not return, just continue. We don't need to calculate that path. Otherwise, we do. So we do vector of int per is going to be equal to frequency, which is going to be one of the arrays in our set, one of the vectors in our set. And we're going to do, what are we doing here? So mem of I plus candidates j dot insert. Here we're gonna do cur of j because we're using that candidate plus plus, and we insert cur in there. And this won't make it twice. Like if it's already there, it's not gonna insert it again, which is good. Okay. And at the end, we basically return the set as a vector. How to convert a set into a vector. Okay. Return mem of target dot begin, mem of target dot end. Okay, so basically we're starting at 0, and then we're adding the candidates to each of the options. And then we're just building on set answer. So, okay. We have 0, and that's going to be equal to an empty array because we don't take any options. Then we branch. Actually, we can do this with a queue so we're not exploring the indexes that we don't care about. So we don't need to do this. That's kind of an optimization. It's not too big of an optimization, but optimization nonetheless. Okay, I mean, we're just gonna pass it this for now. We'll see if it works or not. Init. Novella conversion from I didn't initialize that. Because I don't need to, I believe. What's it say? Is this a runtime? No, it's a compiler. Non-load candidate template ignored. Oh, this should be vector of int, which is what we're gonna end up returning. We'll see. Okay. Zero, 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 one. Oh, Right, that makes sense. So these are the correct answers, but we need to convert them into what it's expected of us. Okay, so for each of the things in our vector, so we're just gonna copy this, basically. Can we return them in any order? Yeah. Okay. So for everything in our set, vector of int ants, and okay, so for each of the element int I equals 0, I less than frequency dot size, which is basically candidates dot size, and I plus plus ants dot push back two things here, and then for this is so inefficient. Okay, int o equals 0, o less than frequency I, o plus plus, or basically ants dot push back candidates I. We're pushing it that many times. And this is for each of the solutions. We kind of need to create an intermediate vector per, and this is per the pushback candidates I, and at the end ants dot pushback per. And here we return ants. Let's see. And this is going to be mem of targets, actually. Okay, I'm fairly confident this is not going to pass. There's no way. It passes. Okay. Somehow. I don't know, I write spaghetti code and it works. Okay, so this, not a good way to solve this. No, it's so inefficient. Like, good thing that there's only like 40 possible candidates. But inefficiency is here. We are storing copies of every possibility. So memory, we're just storing every possibility in a vector and then putting that in a set, and then using that set to create this other thing. Like it's very inefficient. And I think that's because of the way I wrote the solution. But it shows that you can build it in BFS form, like bottom up. Just don't do it. Okay, we're gonna do the we're gonna do the recursive solution. Okay, and I'm gonna write it just in the same file. So okay, what is our DFS? So void DFS Okay, so for our DFS, we definitely need the candidates. We need our target, and then we need the vector with the current elements we've tried. So this is our current frequencies, basically. And it's going to be very similar solutions, just less inefficient because we're not copying over and over. And then I'm going to read the solution and I'm going to find that there's a way easier version, but whatever. We're also going to have here our sets of vector of int. It's just basically going to be the same vector of set of vector of int. This is going to be very similar in this part. Actually, can I just copy like this? I'll just copy that. Okay, and basically we're gonna run BFS of candidates, target, and cur is just gonna be a vector of int of size, candidates of size, and initialize with all zeros. And then at the end we're gonna return solution for target. Actually, solution for 0. So how can we get to 0? Because we're gonna basically decrease target as we go through our DFS. In our DFS, if we also need a sum. Okay. Wait, no, there's a target. If our target is equal to 0, then we do our solution dot insert solution dot insert cur. I hope that like copies it over. There's gotta be a way to not keep all the intermediate solutions. I'm basically redoing the whole thing. The only thing that we're saving here is that cur is not gonna be copied. Okay, you know what I'm gonna do? I'm gonna read the solution and I'm gonna see where I could have done better. Because I could keep doing this, but I feel like it's not good either. Solutions. Let's do like a C++ one. This one has a video. How do we make sure this is unique? Yeah, so this is basically what I was gonna do, which is the backtracking. Wait, no, this is different than how I was gonna do it. Hmm. 2 to the n. I guess the solution is very inefficient anyway. Okay, why is solo leveling in my LeetCode? Just give me a solution, man. Yeah, it's just backtracking. But it's keeping a vector event. Like, I can't see the trick where they consolidate the results at the end. Sort the candidates. How do you distinguish between 2 and 3 and 3 and 2? Target equals 0, results of pushback path. Target less than 0, return. From my start to candidates.size, pushback candidate's I, and then pop back. Okay, but how is this guaranteed to be unique at the end? Return result. Where is result? You pass it in here. Oh, you guarantee to be unique because of the way you test things, because you're doing like you're doing all the possible 2s and then all the possible 3s, and so you're never gonna go back to 2. So you're not gonna do 2, 3, and then 3, 2. It's just because of the way you're checking. How was I building my solution? And this is only, it's not saving any intermediate solutions, because that is the path. Okay, let me try to replicate that. So, solution, it's not gonna be this, because we're not gonna have a set. We're just gonna have a vector of int. And we're only gonna keep it for basically just the solutions at the end, like just for the final solution. And here, do we have to sort it? Yes. Like, what happens if we do like 6 first, and then 2, 2, 2? Does it matter? Why does it have to be sorted? I mean, this guy doesn't sort the candidates. Yeah, this person doesn't sort the candidates either. Okay, so it might be fine. Okay, so if my target equals 0, that means we've reached the solution, so insert the current. Now, if my target is less than 0, that means we went past, so just return. And then otherwise, also because of the way we're doing this, we're gonna keep a current, which is the current integer we're checking from the candidates. So for int I equals cur, I less than candidates.size, I plus plus, and then here we're basically gonna say cur the pushback candidate's I, and then we're gonna say DFS of the same candidates. That doesn't matter. We're gonna keep the same cur because we're trying the current element. And then our target is gonna be target minus candidates I. How do we remove the pop back? Yeah, pop back. Target minus candidates I, and then cur, we're gonna pass. Oh, we have two curs. Okay, let's call this path, like the other person called it. So path the pushback candidates I. And then we're also gonna do path the pop back. And then we're gonna try just moving on to the next element. But moving on to the next element, yeah. Okay, so not like that. We don't need this for loop here. We push back the current candidate, we try with the current candidate, we pop it back, and then we try without putting the current candidate at all. So cur +1, and then target stays the same, and then the path stays the same as it was before. IDX equals array size or remain less than 0. Oh, okay, that's the other edge case. Or cur is bigger than or equal to candidates dot size. Then we return. Okay, let's try that. Blah, 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 blah. So we have the vector of int, which is our solution. We have our combination sum, that's basically going to run DFS, and then we're going to return the solution. If target equals 0, we insert path. Maybe user is not authenticated. Oh, I got logged out. Nice. Okay, and then when we do the beginning call, it is that 0 target and a vector. And also this is going to be an empty array, an empty vector. It's the new vector int, I guess. That's probably not going to work. Can I do this? Or do I have to actually create a variable? Okay, I guess I have to actually create a variable. So int temp equals that and that, and then temp. Not insert, we're gonna say pushback. I is not identified. Okay, candidates cur. and then candidates Kirk. Okay, and we submit. And there you go. Okay, let me copy this. So, okay, basically I tried to do a solution. There's two ways you can usually approach TP. You can explore the graph in a DFS way and in a BFS way, and sometimes it's better to explore it in a DFS way, and this is one of those times. And I like doing the BFS approach, which I did at the beginning. It worked, but not ideal. And here, since this is a backtracking problem where you have to find every possible solution, you should use a DFS instead of a BFS. And what we saved in that process was the memory. Because if you're doing the BFS, you start from here, and then you add 2, and then you add 3, and then you add 5, and then for this, you add 2 and 2. You're keeping, because you're doing all of these at once, you're keeping all of these intermediate solutions, you're storing them inside, like a vector, because you have to keep them all separately because you're exploring them all at once. If you do a DFS, then what you're doing is basically this: that, 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 then you explore this, you find that this is not a right solution. You're basically exploring like a subtree at one, like a whole branch at once, and then you explore the next one, then you explore the next one. So you don't need to store all the possible solutions, because you can just build the solution and then backtrack. So basically, to backtrack, you just remove this element and then try a new one, and remove this element and try a new one. So you only keeping track of one branch at a time instead of keeping track of multiple. So you save some memory there. But yeah, this is basically what we're doing. Like, we're trying an element as many times as we can. So here you would also have like 2, 2, 2, 2, until you get past the amount, which was 7, and then you backtrack, and then yeah. DFS was better in this way because you're not keeping track of all the different branches at once. And then our optimization was that if you're looking at elements in the array, like this one first and from the candidates, then this one, then you don't have to worry about duplicates. Because the way I was doing it was like, you add like the possibilities for 2, and then since I'm adding all the possibilities, then I have to keep track of like how the frequency, so I'm not like repeating 2 and 3 and then 3 and 2. In this way, we don't have to worry about that. But yeah, we solved it. We figured it out. We found that there was a better way. So now I'll keep in mind for the next time that when we're doing backtracking solutions, use a DFS. It's better than a BFS. BFS works for everything else. For backtracking, we have to find all of the possible ways to solve the solution. Use DFS. All right. Well, that is going to be it for me. Let me just try to do a write-up for these, but it's going to be very bad and very broad. Idea. This is a backtracking problem. We have to find all possible ways to reach target. Below are 2 ways to solve the problem. The first is a BFS, and the second is a DFS. DFS is always better for backtracking problems because we don't have to store all intermediate solutions at once. We can use one single array to store the intermediate solution and then reuse it. Okay, this is the general explanation. Our sub-problems for this backtracking are all of the amounts between 0 and target. We use those intermediate solutions to see which branches reach our target. Our base case is amount 0, which we can always get by taking no elements from candidates. Okay, so don't keep exploring branches that are above target. Useless. This is not efficient because we have to copy the frequency array for every intermediate solution. Because we are deduplicating the solutions by keeping a frequency array, frequency vector, we have to compute the actual solution vectors they ask for from the frequency vectors. Okay, and then, okay, let me just label this as BFS solution. BFS solution. We try to insert the per element as much as we can to explore that branch. Then we move over to branches with the next candidate. This is our backtracking step. Check next branch. This is explore current branch. Okay, I like that. And then the other problem we solved was this one. Okay, so idea, run binary search twice. Once to find the beginning element of our possibly rotated array, and another time to run actual binary search on the rotated array, of which we know the starting index now. We use modulo to run to compute the rotated index for our second binary search. Okay. If our right half is sorted, then the first index has to be in our left half, current element included. If our right half is not sorted, then the first index has to be in the right half, not current element not included. Rotated binary search using modulo. Okay. Yeah, today was a hard day. It took me 2 hours, but we figured it out, so that's good. This is the console logs number, what is it? 27. All right. Okay, that's gonna be it for me today. Thank you everybody for joining. I'll see you on Wednesday to keep working on the RAG agent project. And then I'll be back after that on Saturday to do a LeetCode contest. But anyway, thank you all for joining, and I'll see you